Let's look at the covariance of two random variables. We know how to find the correlation between two sets of data, like the height and weight of individuals. We can do that in the TI. But how do we find the correlation between two random variables? Recall that the variance of x is the expected value of x minus mu squared. In other words, it's the expected value of x squared minus the expected value of x squared. Similarly, we define the covariance of x and y as the expected value of x minus mu sub x, y minus mu sub y. Notice how similar this formula is to this. You're just replacing one of those x's with y's. In other words, it's the expected value of xy minus the expected value of x times the expected value of y, or it's the expected value of xy minus mu sub x, mu sub y. So notice how similar this formula is to this one. So expected value of xy is like expected value of x squared, and mu sub x, mu sub y, that's like the expected value of x squared there. Okay, so that's how we define the covariance. What on earth does the covariance mean? Well, if the covariance is greater than 0, that means as x increases, y tends to increase. This would be an example of what that looks like. Situation we have like this. If the covariance of x and y is less than 0, that means as x increases, y tends to decrease. So your data points might look like this, or basically that would be the relationship between the variables. Now, the covariance of x and y is 0 means that as x increases, we cannot say that y tends to increase or decrease. So what does covariance remind you of? Correlation. In fact, the correlation rho between the random variables x and y is defined in this way. Rho sub xy is the covariance of x and y divided by sigma sub x, sigma sub y. So correlation is just the covariance, but the scaling factor of sigma sub x, sigma sub y, those are constants, so that the correlation is always between -1 and 1. Now, suppose, for example, x and y are continuous random variables with joint PDF f of x, y equals 3x, where 0 is less than or equal to y, is less than or equal to x, is less than or equal to 1. Find the covariance of x and y. Let's sketch the domain of x and y. Some books call this the support. This will help us to write the integral. So again, this would be y is less than or equal to x for x between 0 and 1. So this is what our domain looks like. The domain of f is just that triangular region. Okay, so the expected value of x and y is the integral of xy times the PDF, f of xy. So in other words, it's xy times f of xy, which is 3x. And as for the limits of integration, the reason we have those limits of integration is that's the region we're integrating over. This is y equals x. This is y equals 0. So y goes from 0 to x, and x goes from 0 to 1. And that's what leads us here. So y again goes from 0 to x, and x goes from 0 to 1. When we evaluate this integral, we end up with 3/10. Similarly, the expected value of x is the integral of x f of xy over the domain, which works out to be 3/4. And the expected value of y for this function, that's the integral of y f of xy, and that turns out to be 3/8. So the covariance of x and y, the expected value of xy minus the expected value of x, expected value of y, so that's 3/10 minus 3/4 times 3/8. And that all works out to be, once you do the math, 3 over 160. So that's the covariance of x and y. Here's an example, 2015 Society of Actuaries Sample Exam P, problem 104. A joint density function is given by f of xy equals kx. 0 less than x less than 1, 0 less than y less than 1, and 0 otherwise. Calculate the covariance of x and y. Okay, the joint density function is given by f of xy equals kx for x between 0 and 1, y between 0 and 1. Here's the formula for the covariance, so let's go ahead and calculate those. So the covariance, again, is the expected value of xy minus the expected value of x times the expected value of y. We know how to calculate these. The expected value of xy is just the integral of xy times the PDF f of xy. In other words, it's xy times kx. And again, we're integrating over the region where x and y range from 0 to 1. So when we evaluate that integral, we get k over 6. Similarly, the expected value of x, that's going to be the integral of x f of xy. In other words, x kx. Both x and y go from 0 to 1. That works out to be k over 3. And then also the expected value of y is the integral of y f of xy, and that works out to be k over 4. So the covariance of xy is the expected value of xy minus the expected value of x, expected value of y. And looks like that turns out to be k over 6 minus k squared over 12. Oh my goodness! That's not one of the answers that the Society of Actuaries gave us. Look at those answers. They wanted answers that are numbers. These answers, they don't have any k's in there. Okay, so what's the problem? We need to evaluate k squared somehow. Well, actually, we need to evaluate k somehow and k squared. Now, again, what value of k would make f of xy equals kx a PDF? Because, yes, I know they defined f of xy to be kx, but even though they didn't tell us what k is, we can find what k is. And the way we find k is by figuring out the value of k that makes this a PDF. Okay, we know that when you integrate f of xy over the entire domain, you end up with 1. So the integral of kx dy dx, as x and y go from 0 to 1, is, that's going to be, that works out to be k over 2. And the reason for this is that you end up with, I'm going to skip the details, but you know what to do. I mean, the antiderivative of kx, that's going to be kxy, integrate that again. You can do the math. You're smart. This value, this integral turns out to be k over 2. So if k over 2 equals 1, that means k equals 2. And the covariance of xy is k over 6 minus k squared over 12. Plug in 2 for k, and we end up with 2 over 6 minus 4 over 12, a third over a third, equals 0. So a third minus a third is 0, and thus the answer is B. So the answer is B, 0. Okay, so the covariance turned out to be 0. There's an easier way to do this problem. If x and y are independent, then the covariance is going to be 0. And thus rho sub xy, covariance divided by the standard deviations, that equals 0 as well. Not that we need to know this last part. That's just an aside. This is what we really need to know to solve the problem. Okay, now in a situation like this, if x and y, if the distribution of x and y had a relationship like this, they would be independent. So then the covariance would be 0, and the correlation would be 0. So if we could just show, if we could just show that x and y are independent, then we can conclude that covariance is 0. And we'll do that in a moment. First, a caution. Okay, so if x and y are independent, then we can conclude covariance is 0. But the converse is not necessarily true. We cannot say that if the covariance is 0, that x and y must be independent. Here's an example. Here the covariance is 0, and thus the correlation is 0, but x and y are not dependent. So x and y might have a relationship like this. Now again, if this is the x-axis, this is the y-axis, you cannot say that as x increases, y increases or decreases, but clearly x and y are dependent. Okay, so how can we show that x and y are independent random variables? If the joint PDF f of xy equals f of x times g of y, in other words, this is the marginal PDF of x, that's the marginal PDF of y. If you can show that f of xy equals f of x times g of y, the product of the marginal PDFs, then x and y are dependent. We've seen that before. That's how we defined it. This is sometimes handy, but we don't know the marginal PDF of x or y. It's a little cumbersome. In fact, to find those really wouldn't save us any more time than the other way we did the problem. Here's another way that might come in handy, though. Suppose the domain is a rectangle of the form a less than x less than b, c less than y less than d, and again, we could have less than or equal to here. It wouldn't really matter. I mean, if we had that, that'd be fine. The variables x and y, so again, if the domain is a rectangle of that form, the variables x and y are independent if and only if f of xy equals some function of x times some function of y. And in the previous problem, the domain was rectangular, and it was of the form, it's of the form x, 0 less than x less than 1, 0 less than y less than 1. And f of xy is kx, which is some function of x times some function of y. So it meets all the criteria. Rectangular domain of this form, f of xy is a function of x times a function of y, so x and y are independent, and their covariance is 0. So if you know that, man, that can save us a lot of time. We can avoid evaluating several double integrals.